Okay, hello class. Okay, today we will move to the next chapter, which is solution thermodynamic theory. Okay, in this chapter, I divided it into two parts. For the first part, we will cover on the concept, on the introduction related to the solution thermodynamics. And for the second part, we will move to the application of one of the criteria in determining the solution thermodynamics, which is the fugacity and fugacity coefficient. We're gonna do a lot of calculation and go through the example related to that criteria. Okay, the important of solution thermodynamics to be studied is for us to develop the fundamental application in the solution thermodynamics, such as on the mixture of gas and the ideal solution. Okay, it can be applied in the petroleum, chemical process, and also the pharmaceutical, because most of the industry are dealing with the multi-component that leads to the mixing or separation process at the mass transfer rate among the component in the process design. Okay, as the introduction, the real system, okay, when we apply it to the industry application, usually it's contain a mixture of fluid or multi-component. The main or the primary criteria or the variable for the multi-component is due to the composition. Okay, the composition can be related to its chemical potential. Okay, the chemical potential describe the energy transfer due to the change of mole composition. Okay, example, the mathematical expression for the chemical potential is mu, or the chemical potential is denoted by mu I, that's mean for the species I equal to, we can express it based on the Gibbs energy, or dou G over dou N, or the changing of the mole composition at constant temperature, pressure, and the other components, or maybe J, which is not similar to the component of I. Okay, the next properties is partial properties. Okay, partial properties is describe the changing of the overall thermodynamic properties due to the changing of this mole composition, or it denotes by M over bar for the species I equal to dou M, or the total properties, thermodynamic properties, over dou N I T P and J, or is not equal to the I. And the next is we will also cover in this topic about the fugacity. Okay, fugacity is a measurement of chemical potential, or denoted by F, and then later we're gonna learn about the fugacity coefficient over P. So it measures to overcome the limitation of chemical potential by adjusted the pressure in the system. Okay, I will explain to you later about the fugacity. And next, we also will cover on the ideal solution. The ideal solution, which is the ideally behavior of the solution in the related to the mixture of fluid. And we also will move to the access property. Okay, previously we have learned about the residual properties. Okay, the access property is analogous to the residual properties. Okay, previously the residual properties equal to, or the difference between the actual or the real system to the ideal gas. But for the access property, we will discuss more on the ideal solution. So also will be introduced in the composition will be introduced to this criteria. Okay, to move to the learning outcome. Okay, in this topic, in this part, we will cover only 3 topics or 3 main topics. Okay, for the first topic, which is the fundamental property relation. Okay, you should be able to define the concept of chemical potential using the based on the fundamental property relation. In this topic, we will focus more on the Gibbs energy, VdP, VD over SdT. And then the second topic is partial properties. First, they define what is the partial properties, and then how to correlate the partial properties and chemical potential, and then last to define the partial properties in binary solution. Since we focus on the binary solution, describe the solution properties, partial properties, and pure properties in the, usually we will compare this or describe the properties using a graphical. Later we will further discuss about this. And then last is the concept of fugacity. So we will touch a bit or the introductory of the fugacity and why the fugacity is introduced in this topic or solution thermodynamics. Okay, for the first part, in a closed system, okay, if referring to the Gibbs energy or generating function, okay, we can have a dg equal to vdp minus sdt. Okay, this is the common relation of the Gibbs energy. Okay, by considering the number of mole into this expression or the correlation, we can obtain the d and g minus nvdp minus equal to nvdp minus sdt. So why we consider on the number of mole? Because we will try to relate it with the composition. Okay, and then once we perform the Maxwell relation, we can define the specific or the molar volume and also the entropy based on the example. For the molar volume, it equal to the dou Ng over dou P at constant temperature and number of mole for the certain species, and also to determine the entropy, we can obtain it from the dou Ng over dou T at constant pressure and number of mole. Okay, how about if we have a system that consists a single phase and open system? Okay, back to the fundamental or the concept of in thermodynamics, we have a system and also surrounded or across the boundary, we call as surrounding. So for the open system, the matter can be whether living or insert into the system. That means that matter can be across the boundary. That's why from the previous expression, we add another term, or we determine or describe the energy due to the change of mole composition at constant pressure, temperature, and other composition that we described earlier in this term. So this term or the additional term that we insert is called as chemical potential. Okay, let me explain further about this. Okay, since this involved with the submission, you should consider how many component in the system. Example, in our system, we have 3 components. So for the first term, it minus d over dou 1 at constant temperature, pressure, and constant component 2 and 3. Okay, for the second component, dou, if we consider the mole, so I should include the number of mole or the G as well. So dou Ng over dou N2 at constant temperature, pressure, and component 1 and component 3. How about for the third component? Okay, so we use the same description, but we change the component for change on the composition of component 3 by constant the temperature, pressure, and component 1 and component 2. So sum up all this, the value, it can give the chemical potential for the system, in the system based on the given information or the problem to be solved. Okay, we already defined the chemical potential, or it can denote by mu I. Okay, the fundamental property relation for single phase fluid system of constant or variable composition. So this is the variable composition and constant T and P. Okay, for the special case, which 1 mole of solution or N for the solution equal to 1, or we can obtain it, N for the mole for the species equal to composition. So we can replace from the composition to the species. So, and then when we explain it or further describe it based on the functional, so for the Gibbs energy equal to the function of pressure, temperature, and the composition. And then based on the Maxwell relation, we can obtain the molar volume and the entropy from the Gibbs expression, which Gibbs is expressed as function of its canonical variable. So the canonical variable for Gibbs are pressure, temperature, and composition. Okay, as we have covered previously, each thermodynamic property such as enthalpy, Helmholtz, we have learned about the entropy. It has own canonical variable or function. Okay, you can list the function like, okay, express the function like this expression. Okay, and next, how about if the system having two phases in equilibrium? So, example, we have but two phases or denoted by alpha and beta. So we can consider the phases to describe or express the mathematical expression in the system. So for each composition, the total of thermodynamic properties equal to each composition. Example, V equal to V at liquid plus V at vapor. Example. So to replace it, or if we perform the mass balance, we can obtain the chemical potential for each phase has the same value at constant, or if we have the constant temperature, pressure in equilibrium. So if we perform the balance. Okay, let's take a break a bit. Okay, let's test your understanding. We have a system. Water is added in a beaker at maybe the temperature given here at 80 degrees Celsius and 1 atm. Okay, the chemical potential of water in a liquid is 60 joule per mole. Okay, example. So chemical potential you can denote by, oh sorry, not alpha, but mu. We can denote by mu. So mu of water in liquid. Let's say, okay, this is for the liquid. What is the chemical potential in vapor? In the beaker that have been the same temperature and pressure. So to test your understanding, I think that you can answer it if you understand it from the previous explanation. Okay, I believe you already have the answer for this question. Okay, so since the system, or we can consider as in equilibrium, so the potential chemical potential in the liquid phase equal to the chemical potential in vapor phase. So the chemical potential in vapor phase equal to 60 joule per mole. So we can get the answer. Okay, next topic. Before we further explain about the partial properties, let's have understanding on the definition of the solution and also the what is the properties in the categorized under the thermodynamic or solution thermodynamics. Okay, the word solution. Solution does mean it contains the mixture of two or more species. So the phase of species, whether we have the liquid, gas liquid, gas, or solid liquid. But in this topic, we will focus on the liquid, or we have the binary system. Okay, there are three types of the property in solution thermodynamics known as first solution properties or denoted by M. And that's mean the thermodynamic properties. In describing the thermodynamic properties, it can be either Helmholtz energy, or we have entropy, or Gibbs energy, or internal energy. So, or we have this enthalpy. And the next property is partial properties, is denoted by M over bar for the species I. And you can replace it based on the properties mentioned or described in your system. For the pure species or the last species or denoted by Mi. Example, in the system, we have two components, or the system is a binary solution. So we have M1, M2. So in describing your system, maybe your system is you intend to describe the system based on the entropy. So it turns to entropy 1 and 2. Let's take a look on the example of the partial properties. Okay, this system consists of liquid, or the phases is in liquid, and that it has a two component. The composition of component 1 is given as 0.6, and the second component is 0.4, should be 0.4. And then the volume of the system 1 is 1 liter. Okay, and then the second or the final volume is 1.0015 once we added a small amount of compound 1 into the system. So to solve the partial properties, or since the system is based on the thermodynamic properties of species, equal to the difference of this total thermodynamic properties in the solution over the mole composition at constant temperature, pressure, and J. Example is not equal to Ni. So back to the case here, we have V. This is V initial and V final. So we can determine the difference of V. Okay, if we compare to this problem, so we gonna use the molar volume as our properties. So it tends to have since it added the component 1, so V1 or partial molar volume equal to the difference of the volume over difference of composition of component 1 at constant temperature, pressure, and also the other species that 1. So that's mean the species here, it should be N2. So the species is N2. Okay, the delta V. So we have 1.0015 liter minus 1 liter over the mole is 0.001 mole, and it gives the value is 1.54 liter per mole. So the partial properties can be defined as the difference of the thermodynamic properties due to the change of the mole composition of the species. So that means we need to refer to the mole composition. Okay, let's take a look on the other example. So how about if we have comparing the ideal solution and also ideal. So let's consider we have a beaker and then it consists of the toluene and benzene. So 1 mole of toluene, okay, equivalent to 106.4 mil. Okay, this is based on the molecular weight. So I consider that the volume is based on 1 mole of its molecular weight. So, and then for another component, we have 1 mole of benzene, or equivalent to the volume is about 88.9 mil, and then the total is 195.3 mil. So once we added the same amount of the toluene and benzene into a beaker to perform the experimental work, so we can obtain the same amount that we calculated from this based on the equation. So we can say that the volume will be increased as we added the volume of species or the component into the beaker. How about for the non-ideal solution? Okay, what is the difference between the ideal and non-ideal? For the ideal solution, that means it has the chemically same species, right? So whether the shape is similar or it comes from the same group, or it has the same size, so we call as ideal solution. But when we refer to the non-ideal solution, that means it has the different chemically species. Okay, example, maybe I give you a simple of ethanol and water. So 1 mole of ethanol, okay, denotes by E, is equal to 58 mil. And also based on its molecular weight, and 1 mole of water, it has 18 mil. So once we add this, so we can have this 76 mil of the volume. But when we perform the experimental by adding the same amount, so the volume is less than 76 mil. So maybe we obtain about 74.3 mil. Okay, firstly is due to the interaction between the component. Second, the total volume can be determined by considering on the partial volume. So we have the partial volume 1 and partial volume 2. That's mean for component 1 and 2. Example, we name or we consider, okay, we assume that ethanol as component 1 and 2 is for water. So to determine the volume is number of mole for component 1 times V1, or partial volume for component 1, and 2 partial volume of component 2. So from the given the partial volume is, example, we obtain the partial volume is 57.4 mil, and then for second component is 16.9 mil. So you added this summation of both partial volume. Okay, example, the number of mole is remain the same, 1, so we need to times this, and then 16.9 mil, it gives us about 74.3 mil. So the volume from the calculated here, so in determining the total volume, we should use or refer to the partial volume instead of calculate the theoretical value from the molecular weight that to obtain the exact or to obtain the real total volume based on the real system. So later I will show you another example how to determine the mole fraction is not if it's not given into the system. Okay, in conclusion, we can conclude that the solution properties is a properties that represent the solution as a whole mixture. So whether it has a two or more species, so we combine everything. So it gives us the calculation as N1. So consider, so if we have a 3 example, so if we have a 3 component, so it based on the whole mixture. So regardless you have 3 or more species. And then partial properties belong to the species that exist in the solution. So it can determine from the differentiate or different or the changes of the thermodynamic properties due to the change of its mole composition. Next is the partial properties. Properties belong to the species that exist in the solution, or in the detail, we can define it as any extensive property of a solution change with respect to the number of mole at constant pressure, temperature, and other species. Okay, the extensive properties, that mean the properties is dependent on the size of the system. Okay, the pure species properties is the properties of the individual species as they exist as one or pure state without the presence of any other species at same temperature and pressure in the system. Okay, let's move to the detail of the partial properties. Okay, we have defined the chemical potential based on the chemical potential is based on the different energy transfer, or refer to the Gibbs energy over or due to the change of the mole composition at constant temperature, pressure, and the composition of other species. And if relate to the partial properties is based on the difference or change of the thermodynamic properties of the solution due to the same as the meaning for the chemical potential, which is due to the change of the mole composition of species I by constant the pressure, temperature, and the composition of other species. So when we compare between the potential, chemical potential and the partial properties, we can conclude that it has the equivalent, or if the thermodynamic properties is based on the Gibbs or partial Gibbs energy, the potential chemical is equal to the partial Gibbs and partial molar Gibbs energy. For any thermodynamic properties, we can express the function like this expression. So we have the thermodynamic properties by considering the number of mole equal to thermodynamic properties as function of temperature, pressure, and also the mole composition for the species or the particular species. Or if we differentiate this, it will turn to this expression. So we have the D and M, and then we have this. First, we constant the temperature and vary the pressure, and also second, we constant the pressure and vary the temperature. And the last is we investigate the changes of the mole composition by constantly the pressure, temperature, and composition of other species. So these are the general equation describing the thermodynamic properties, how to relate it with the Gibbs function or generative function from the Gibbs energy. Okay, in mole fraction, we can obtain the replace this term to the partial property. So we can have this expression to describe the thermodynamic properties at constant, or if we have the based on the pressure, temperature, and also the mole composition. Okay, the chemical potential is a driving force because, okay, based on the definition or mathematical expression here, we can describe it describes the energy transfer or relate to the measure of work of a system when changed in mole composition. Example, the chemical reaction of mass transfer in the system. Okay, from the previous expression, okay, we will derive this equation to obtain the Gibbs-Duhem equation or relate it between the solubility relation and also the partial properties. So we can derive this first to have this expression, and then second is replace this term to the expand of the from the derivation, and then we can have this expand. Okay, just replace this to the another expression, and then we can perform the or rearrange this term. Okay, you can see we have n at the end. Okay, maybe I write up n first. So n, and also we have n, and we have n. So we can rearrange to have the dn and the dn, because okay, for the n, that means we have one system that we can choose the system but fit the size. Okay, for dn, that means we have a variable size in the system. So you can rearrange to have this n and the function of the dn of different mole composition. And then, so we're gonna have first term and the second term. So both term is equal to 0, or we can, okay, for this second term is equal to the solubility relation. It can express by total of the thermodynamic properties equal, or the thermodynamic properties equal to the summation of the composition time is partial properties. And also we also can have this relation if we based on the number of mole, and this if we have this composition in the system. Okay, for the first term, we can rearrange it to put the dm at the front. So from this equation, we can differentiate to obtain the delta m. So it's similar to the first term. So you can see we have the similar, and then you can compare between both. It gives us the another equation known as Gibbs-Duhem equation. Or at constant temperature, or if we constant pressure and temperature, so the remain is summation of composition times the partial properties equal to 0. So this is for the special case. Usually we can use this equation to determine the partial properties. Okay, let's move to the next. Okay, we will focus on the binary solution. Binary, that's meaning in one solution we have two species 1 and 2. Okay, back to the solubility relation. M, or the thermodynamic properties, equal to summation of composition of species times the partial properties of the species. So we can expand it since it we has the binary, so we have component 1 and 2, so it give us the total thermodynamic properties equal to component 1 and plus the component 2. And then when we differentiate it, we can have this expression. So you can also rearrange this equation to have this m equal to my. So that's mean I can write here m equal to x1, so remain one only, one variable only, plus 1 minus x1 m2. So you can rearrange it to have m minus x1, or if we have based on the, or if we consider based on x2. Okay, example, we can rearrange this binary solution to have only one variable, whether the component 1 of the variable for component 2. It's easier for us to solve the problem. Okay, let's take a look for this is the binary solution from the summability relation. So we can rearrange it. So example m x1 m1 plus 1 minus x1 m2. So we can rearrange it to have this x1 m1 plus m2 minus x1 m2, or you can have this m2 minus x1 and m1 minus m2, or you can have this. Another is, okay, we have, okay, plus x1, and this is the, if you decided to choose the x2 instead of x1, so you're gonna have two expression, or depend on the given component in the problem. So basically, what the main purpose is to simplify the equation and to minimize the unknown variable in the system. Okay, special equation from Gibbs-Duhem. We have this equation based on the partial property or submission of the partial properties of each species equal to 0. And then we can also perform based on the binary solution, and then we can compare between these two lines. Okay, the detail to define it. First, we need to prove that the partial properties can be obtained from the graphical method. Okay, first take a look on this diagram. Okay, we have these thermodynamic properties against the component 1. Okay, example, the required us to determine the partial properties at this point. The mole fraction is given, and then the line, okay, red line here is the value of this when we the data that given by plotting the thermodynamic property of the solution over or against the composition of component 1. So in order to determine the partial properties at this point, first we need to draw a straight line. So to cross this point, so maybe you can drag until the x or the pure component of species 1. Okay, and then if you can see here, we can determine the value of this variable, the partial properties from the slope. Okay, you can choose the color. Okay, these are the ds1, and then you can get dm. So dm over ds1 equals to m minus I2 over x1. So this is the slope is over S1. So you can get the value of S1. Or if you extend the line up to here, dm dx equal to 1 minus I1 minus I2. So you also can use this slope example. Using this, or because you need, okay, so you can use this slope as well. So we can have this total I1 minus I2, and you can obtain the slope of the dm over ds1. Okay, so we have two expressions. Okay, so first we need to rearrange this equation to be insert I2 into this equation. Okay, I2 equal to, okay, let's rearrange this. So I2, maybe I start with dm over ds1 equal to m minus s2. So s2 dm over ds1 equal to m minus 1 I2. So I2 give us this m minus s2. Oh, sorry, s1. Okay, that should be s1. S1 dm over ds1. So you can have this expression m minus, and then you can replace into this I2. So that's why we can obtain this this arrangement or the expression to give the expression for I2 and I1, and we can compare with the previous expression that we obtained from the for the binary solution between the Gibbs-Duhem equation and also the derivation of the expression to the overall the express the okay, we can relate it between the we can compare it between the between this expression to the expression that we proved previously using the correlation between the summability relation and Gibbs-Duhem equation. So we can see here I2, or it can also denote by partial component 2 equal to m, so having the same, and s1 dm s1. Okay, for the second or the component, for the second term or the component 1 is m plus s2. So it equivalent because 1 equal to s1 plus s2. So we can conclude that the partial properties also can be obtained from the slope of tangent, or the based on the based on the slope from the graphical data, graphical from the plotting of the solution of the solution properties against the composition of respective component. Okay, these are the detail about the graph. So we already discussed about the how to. We already proved that the point of I2 can be also represent the partial properties of component 2. And if we have the straight line, for example, this is our point and the straight line, we can also obtain the value of I1 minus I2 that previous we have proved earlier, and it gives the partial properties of component 1. Okay, the second is related to the infinite dilution. Okay, for the infinite dilution, okay, I would like to, maybe I can explain a bit more about infinite dilution. Let me, okay, for the binary solution, Okay, referring to the Gibbs-Duhem equation, we have as I d mi equal to 0 at constant temperature and pressure. So for the binary solution, we have this x1 dv1 plus x2 dv2 equal to 0. So we can simplify these to having one variable only plus 1 minus x1 dv equal to 0. So rearrange it to obtain x1, or we can differentiate based on the dx1. So it turns to x1 dv1 over dx1 plus dv2 over dx1 equal to 0. So if the solution, or we have the infinite example for infinite dilution of, maybe we start with the species 1 equal to 0. That means species 2 equal to 1. So if we have the infinite dilution for component for the species 1, you can refer or insert to this. We can have dv2 over dx1 equal to dx1 dv1 over dx1 and divided by times 1 over 1 minus x1. So it gives us the minus x1, 1 x1 dv1, dv1 and dv1 over dx1. So dv2 equal to dx1. So if we have the infinite dilution for x1 equal to 0, so that means it has the opposite sign. So you can see that for m1, so if we have infinite, or for s1 equal to 0, it's gonna have m1 or infinite, or the partial infinite of thermodynamics. So that's why, okay, back to the slide, that's why we're gonna have the partial for infinite dilution. We're gonna have the partial at it depends on the solution, or the purity of the solution. That means if we have the system that contain the pure is the component 2, that means the partial infinite dilution is referred to the component 2 due to the opposite sign. Okay, as conclusion, the intercept of tangent give two partial properties. So it whether based on the component 1 or component 2. So m as 1, or the partial component 1 equal to at component 1, and m for the partial component 2 at x1 equal to 0, or we have x2 equal to 1. Okay, the intercept value will change as tangent point varies along the curve until it reaches limitation or limiting value. So example, if we consider the x1, or the species pure, the pure species is component 2. So that's mean the partial properties will be equal to the solution at component 2, because we use this mi equal to summation SIM. So we gonna use this based on the component. Okay, the opposite intercept, that's mean we referring to the equation that it has the different or opposite sign. Example, d m partial 2 dx1 equal to minus dm 1 over dx1. So it has the opposite sign. That's why we have this. We have the for the infinite dilution, the partial properties of component 1 will be equal to the partial properties of infinite dilution. So same goes to the other sample. That's mean we have the pure species of component 2. So we can have the partial properties for component 2 equal to infinite dilution of the partial property of infinite dilution of component 2 at constant temperature and pressure. Okay, the example 11.3. The need arises in a laboratory of 2000 should be 2000 centimeter cube of an antifreeze solution consisting of 30% 30 mole percent methanol in water. What volume of pure methanol and pure water at 25 degrees Celsius must be mixed to form 2000, okay, this correct, 2000 centimeter cube of antifreeze. Partial molar volume for methanol and water in a 30 mole percent methanol solution and their pure species molar volume of, okay, the information are given. So the required volume is, 2000. Okay, we call as the total volume. So this is the total volume required in the beaker or in the maybe in the solution, and then what is the total volume of component 1 and total volume of component 2 to be added. Okay, first we need to determine the volume because the V1 total equal to the mole fraction 1 times the volume. So we can get the total volume. So to define the volume mole fraction or N1 equal to the volume, total volume over the volume. So we already have the information on the total volume. So we need to find the volume first. So volume equal to, or this should be V1. So volume equal to S1 V1 partial plus S2 V2 partial. So 0.3, the fraction is partial volume also given. Per mole plus 0.7, 70.765 cm3 per mole, and we can obtain the volume of the volume is, let me do the calculation, is 24.025 cm3 per mole. And then next, okay, we already defined this and we need the total volume also given. Okay, basically this is not for N1 but for the N. So how to determine the N1? N1 equal to S1 plus N. So we need to define N first. So N is, total volume is 2000 over volume 24. Or the is given 83.246 mole. So the total mole of the solution. So the first determine V and then second determine the mole of the solution. Okay, and then we need to determine the mole for each component. So N1 S1 plus times n. So x1 is 0.3, n is 83.246 mole, and then n1 is equal to 24.974 mole, n2 is 0.7, and the total is, the answer is 58.272 mole. And then what else? Okay, finally we can determine the total volume for each species. So V1T equal to N1V1. So N1 is 24.974 times V1 is 40.727 cm3 per mole. So the answer is, let me share, the answer is 1000 cm cube. And then V2, okay, you can use the same. So N2 is N2 times V2, and then the answer is 1052.86 cm3 centimeter cube. So you can, finally we can obtain the volume of pure methanol. So we can conclude that the partial molar properties indicate the individual compound or individual compound in the mixture to determine the overall. Even though we have a mixture, but still we can determine the individual compounds in the mixture based on the partial properties. Okay, so this is the way you can solve this problem. So from the graphical, okay, the graph actually using example to perform the V. So usually in plotting the graph, you should be given the expression. So this is the data obtained from the experimental work. So what I would like to highlight here is the value of this one and also this value. So you may compare to the calculation that you obtain. So example, we have partial 38.6. So example at 0.3, if you can drag and the straight here, it gives you the value of partial value of V1, the component 1. And for this line, we can obtain the value of V2. Okay, for the pure component, for example, V1 is for x1 equal to 1. So that's why we can get the pure component. And pure component 2 is x2 equal to 1. That's mean if we have x1 equal to 0, x2 equal to 1. So from this graph, it gives all the properties. First, the pure component, and then the partial properties, as well as the total volume. So this graph is can be obtained from the relation we have obtained, the expression we have obtained previously, that we can determine that. And from this correlation of this partial and also the partial 2. So maybe that's 1 plus x2. So how to obtain this? You can use your expression we have learned previously. So I would like to just to highlight how can you describe the each property from the graphical. Okay, in the tutorial we gonna proceed or detail the example related how to obtain the graph in determining the in describing the properties in or for the thermodynamic. The last topic is fugacity. Okay, back to the definition of chemical potential, or denotes by mu I. It describes the fundamental criteria for the phase equilibrium numerical values of chemical potential. Okay, the chemical potential is defined based on the Gibbs or generating function that relates to the volume and the entropy, which cannot be expressed as an absolute quantity because we have this, the entropy in the expression. Okay, numerical value of chemical potential are difficult to relate to, more easily understood in terms of physical quantity, which chemical potential is not favorable for phase equilibrium. Okay, based on the limitation for the chemical potential in the system that have been the equilibrium, example for the binary system, it has the same value for all phases. So this is the limitation using the chemical potential. Those chemical potential can be mathematically transformed into developed properties that easier to be used, or we call as the fugacity. Okay, fugacity is invented by G and Lewis in this year that takes place of chemical potential. So because of the limitation of chemical potential, example, if we have a system contain of water, or maybe I can draw in a system containing a water that have been the maybe temperature at 80 degree and 180 m. So the possibility we also have another phase in the system. Example, it will give us the, if we heat up the system, maybe vapor and liquid phase of water is observed here. Okay, if we characterize of this value based on the example, if we characterize this value based on the chemical potential, we gonna have the same amount of the chemical potential for each phase at given temperature and pressure. But for fugacity, at the constant temperature and pressure, it will give the different value of fugacity in vapor and a liquid. So it can be more favorable to be used. Okay, we have learned that fugacity is a replacement to the chemical potential due to the mathematical expression is more friendly to be used instead of having the chemical potential, because for the chemical potential at all phases, it gonna have the same value in an equilibrium. But for the fugacity, it can predict the multi-component that involve any solid and liquid, also gas in equilibrium phase. Okay, it also can predict the final phase and reaction of multi-component mixture at various temperature and pressure without doing the actual task. Okay, the ideal gas law, which is at lower pressure, the chemical potential approaches to the negative infinity. But if we introduce the fugacity for ideal gases state, which is still at lower pressure, the fugacity is approached to zero and the fugacity coefficient will be approached to 1, which we can perform the mathematical manipulation for them to apply the fugacity in the system. Okay, so maybe to test your understanding, you can try to answer why the fugacity is introduced into the system. Okay, for the next topic, we will perform the detailed equation and the mathematical expression related to the fugacity and fugacity coefficient. I hope that you can cover all the learning outcome. Okay, let me summarize. First, we have learned about the chemical potential. what is the definition of chemical potential that describe the heat or describe the energy transfer due to the change of mole composition at constant temperature, pressure, and the composition of other species. And also we cover the partial properties. How can we relate the partial properties to the chemical potential? Okay, the partial properties describe the individual compound in the mixture. Even though we already mix that component or the species, we still can define its individual compound using the partial properties. And the last, we also covered the fugacity. Before we proceed to the next part, the detail about fugacity and fugacity coefficient. Okay, the introduction of fugacity is to replace the limitation of chemical potential, which at equilibrium, the phases of based on the chemical potential is equal to all the phase, or the value is similar at constant temperature and pressure. So to overcome this, we introduce the fugacity that is easier for us to be measured by adjusting the value of pressure. So thank you for your attention. Okay, thank you for your attention. I see you for the next part. Okay, bye.